So in the previous video, we took a look at the definition of relative extremum. And essentially, we decided that a relative extremum, or I guess, examined that a relative extremum is essentially just a critical point at which f prime changes signs and the function f is defined. And so we kind of got a graphical sort of intuition of why this definition makes sense. And, we looked at what would be a relative extremum and what wouldn't be, just graphically, of course. And then we kind of came to this sort of conclusion over here that if f prime goes from decreasing to increasing, then we have a relative minimum, and if f prime goes from increasing to decreasing, then we have a relative maximum. This is, of course, assuming that the actual point at which this is occurring adheres to the conditions we mentioned over here for the relative extremum definition. And so with that in mind, we're going to go ahead and take a look at this kind of formalization, I guess, of what we constructed right over here, and that is the first derivative test. And so the first derivative test tells us that if f goes from increasing to decreasing, so if we have a critical point at which f is defined, and f goes from increasing to decreasing at that critical point, so it changes from increasing to decreasing, then we have a relative maximum. Similarly, if f goes from decreasing to increasing, then we have a relative minimum. Again, we're assuming that at this critical point, f prime, or we're assuming that this is at a critical point and that f is defined at this point. Another way to take a look at it, or another way to think about it, is that if f prime goes from positive to negative, then we have a relative maximum, because if f prime is positive, we're increasing. If f prime is negative, then it's decreasing, then f is decreasing. And so that's kind of another way to restate this condition that we described right over here, is that if f prime goes from positive to negative, then we have a relative maximum, and if it goes from negative to positive, then we have a relative minimum, and that would be the first derivative test. And so let's actually go ahead and do a couple of examples to first of all determine local or relative extremum using the first derivative test. And so here we have f of x, which is this polynomial function, and we want to find the local or relative extremum of this function. And so the first thing to do would obviously be to find f prime of x, or to take the derivative. So f prime of x is going to be 3x squared minus 4x, and that's just using the power rule, right? And this one is going to disappear. And essentially what we want to do is we want to find the critical points. And so we're going to, first of all, check if there are any points at which this function is undefined. And so we know that f prime is defined for all real numbers, right? So this is going to be defined for all real numbers, right? It's just using a bit of shorthand notation. And so we don't really have any points at which we're undefined, but now we need to check if this function is ever going to be equal to 0. So what we can do is we can set f prime of x equal to 0, so 3x squared minus 4x equal to 0, and then we can just see if there are any x values which actually satisfy this. And so let me go ahead, we can factor out an x here, and then rewrite this as x times 3x minus 4, which is equal to 0, and this tells us that x is going to be equal to 0, or x is equal to positive 4 over 3. And so these right over here, these are our critical points, or our critical values. Let me use critical values instead. And so we have two critical values over here. Now we need to actually use the first derivative test, right? So first of all, is f defined at these points? Well, we know that f of 0 is defined, right? And we also know that f of 4 over 3 is defined, right? And why do we know that? Well, because we know that f is defined for all real numbers, right? Because f is just a polynomial function. So for all x is a member of real, or x is a member of R. And so with that in mind, we can now actually go ahead and use the first derivative test, because we've established all the conditions, we have our critical values, we know that f is defined at these critical values. Now we can actually see whether f prime changes signs at our two critical values. So it's usually helpful to kind of draw out a number line. I like to do that. Okay, let me make it a bit smaller and a bit less kind of bent. So here we have our first critical value 0, and then here we have 4 over 3. So this is our number line right over here. And what we can do is we can take any value that's less than 0, right, any value within this region, and input that into f prime and see whether f prime is positive or negative, and it will hold true for the entire region. So let's go ahead and do that. So let's take maybe -1. So let's take f prime of -1. That's going to be equal to what? We have negative times -3 minus 4. And it doesn't really matter what this number is equal to. We know that this is going to be negative, and this is also going to be negative, and so here we end up with, what do we have? We have +7, and so we know that over this entire interval, f prime is positive, so I like to put kind of a positive sign there to indicate that we're positive over that interval. And then let's take some number within this interval right over here, and the easiest one is probably just +1, so f prime of 1, which is going to be 1 times 3 minus 4, which is equal to -1. So we know that over this interval, we're going to be negative. And then finally, f prime of really anything, within this interval, greater than 4/3, I'm going to choose 2. We get 2 times, 6 minus 4, which is going to be 2 times 2, which is 4. And so we're positive over this interval. And so now let's take a look at our little chart over here. We know that f prime goes from positive to negative at this particular point. So we go from increasing to decreasing. And then at the point 4/3, we go from decreasing to increasing, or from negative to positive. And so we can use the first derivative test to say that f has a local or a relative maximum at x equals 0, right? Because we change signs from positive to negative. F prime changes signs from positive to negative, or f changes from increasing to decreasing at x equals 0. And f has a local minimum at x equals 4/3. Why is that? Well, we go from decreasing to increasing, or f prime goes from negative to positive. And so that's how we would actually find these relative extrema. Let's go ahead and do one more example over here. We have this example, f of x equals x over x minus 1. And this is actually a very important example because you're going to come to find that we have a very interesting result over here. So let's first of all go ahead and take the derivative before we even, delve into that. Right, and so the derivative over here, if we're to use the quotient rule, we have the derivative of x times x minus 1. So it's just going to be x minus 1 minus the derivative of our denominator times the numerator, so minus x, over the denominator squared, so over x minus 1 squared. We don't really need to expand that denominator. Here we'll end up with -1 over x minus 1 squared. Now, first of all, let's actually go ahead and find the critical points of this. Well, do we have any critical points? We know that if we were to set this equal to 0, then this tells us that -1 is equal to 0, which is just not true. And so we know that f prime is never going to be equal to 0, so we can't find any critical points that way. So then we resort to the other method. We need to see when f prime is actually undefined. And so we know that f prime is undefined at x equals 1, right? Because the denominator will become 0, so we'll get -1 over 0, and so we're undefined. And so we do have a critical point. So we do have a critical point at x equals 1. But can we actually check whether we have an extremum at this point? Well, let's think about it. If we were to input f of -1 into our actual function, because we have this other condition that we need to satisfy. We need, if we go all the way over here, we need f to be defined at this point. And so although we have a critical point at x equals 1, we know that f of -1 is going to be what? It's going to be -1 over 0, and we're undefined. Or not f of -1, f of +1, and we're undefined. So f is undefined at this point as well, at x equals 1. And so because of that, the only critical point we have, f is not defined at our only critical point. And so because of that, we can say that f has no relative or local extremum. And the reason we know that is because we took the critical points, or we found the critical points, and we input that into our function f, and we found that f is not defined at our critical points, so we can't use the first derivative test, and we don't have any relative extremum.